Okay, and we'll take questions from the audience. So I have a quick question. I was curious, what was the one thing you had to leave out of your presentation because you were limited by 2 minutes?
Yeah, so I was interested in kind of the question, which is, at small scales, is the biology determined mostly by the physics in the region, or is it determined mostly by just kind of purely biological processes? And I was able to look at, it's a structure function framework, so it's basically taking the variance between measurements taken at the same time as a function of distance separation. And they looked the same between temperature, which is an active tracer in the area, and biology, so fluorescence and backscatter. And that kind of led me to believe that at least at the 20-kilometer and under range, biology is determined primarily by the physical field in the area.
Yeah, I guess I would say that I think there's a lot more discussion to be had on the kinds of different spatial and temporal scales of motion and how that can affect nutrient flux. And so maybe more than something that I had to leave out, of something that I'm really interested in discussing is how matching of time scales versus matching of spatial scales contributes to different types of fluxes. So is it more about the local productivity, or is it about the distribution of nutrient anomaly on density surface that matters the most?
May I have the question? Sorry.
What is something you wish you had time to say during your presentation, but you couldn't because it was too short?
Because my study area is really very complex, and I have a lot of work. Actually, those water masses I want to say my study is about interannual variation, but in this slide I didn't talk about that because I have very limited time. Actually, those water masses and nutrient condition in those water masses are changed year by year. So if you are interested, and please, I want to discuss more about that. Thank you very much.
Hi, this is Angel White from Oregon State University. I had a quick question for Mara. You talked about the biomass maxima in oligotrophic regions, and generally the chlorophyll max is not associated with increases in biomass, so I was curious what proxies you were using for biomass.
Yeah, I guess one thing I forgot to say is that this is a modeling study. And so I had complete knowledge of the velocity fields, which is why I was able to do this decomposition. And then I was also using I developed a nutrient phytoplankton model as my biogeochemical model in this model. And so in my case, that was a biomass maximum. And one of the benefits of doing this for that study was that I had a defined layer across which to measure the flux. I think that this kind of work would have been much more complicated, and probably is much more complicated because of productivity happening over a much wider vertical section than a kind of narrow biomass maximum.
So I can see all your nice phytoplankton groups then. We were talking about scale. How small a scale or finer scale spatially do you think you need to go to in the ocean to be able to resolve the patterns of the different groups? Can we get it, for example, at mesoscale? Do you need to go sub-mesoscale or sub-mesoscale? What's your kind of feeling on that?
So I don't know. I've seen a lot of really cool images of really, really highly resolved temperature and ocean color observations from remote sensing, generally from airplanes, not from satellites. And even on like scales of tens of meters, often you will see really, really distinct areas just because of stirring. Now, I don't know if that's a different ecosystem. It might just be stirring of the same ecosystem. But at least to fully capture the physical field that influences biology, I think to fully capture it, you need much, much smaller than a lot of what anyone is doing at, kind of larger scale studies. But I don't know if you need to fully capture it in order to explain it.
It's a very interesting answer, and I'll tell you why I ask it and whether the context is. It's because I'm a modeler. And if you look at the 3D GCMs, for example, even at a 12th of a degree, you're not going to capture what you just described. So even if you had a perfect biological model, unless you have the physics to drive it at the appropriate scales, you can't get the right answer in inverted commas. So it's just something to think about. It's very interesting.
Yeah, so that was one of the questions that I was looking at mine, and I mentioned that I did a spatial decomposition as well. And so when I look at a coherent spectrum, I see a peak at about 10 kilometers and then maintaining high coherence below 10 kilometers. And so my model was a 1 kilometer resolution. And so I guess I would say from that, I think you need to have at least 10 kilometer resolution in a model to be able to resolve this, with the caveat that I was using an extremely simplified biogeochemical model.
Which is a big deal if you're using global models to get down to 10K.
Yeah.
I had a question for Nick, I think it is. Some of the low vorticity features that you saw, it looked like they were propagating downwards at kind of 10 meters a day or so. Is that related to inertial propagation, or why were they doing that? They look very streaky coming from the surface.
Yeah, so I think some of that, most of them go along potential density surfaces. So I don't know if I mentioned, but there were thin black lines on that figure that were potential density surfaces, and they might have been going along that. The other thing is that in general, it's really, so to do potential vorticity, you're taking a lot of derivatives of data. And so it's really noisy. And I think a lot of streaks, especially if they're vertical streaks, might just be a result of noise in the data. So this is not a model. I wouldn't say from looking at it that there's a big downward propagation in a lot of the potential vorticity, low potential vorticity boluses, but yeah.